Double integrals allow us to calculate the volume under a surface within a specific region. While we often think of vertical slices, horizontal slicing is a powerful alternative when the boundaries of our region are defined as functions of y. Sometimes, a region's geometry makes vertical slicing difficult or requires splitting the integral into multiple parts. By switching to horizontal slices, we can often simplify the calculation into a single, elegant integral expression. In horizontal slicing, we treat the region as a stack of thin horizontal strips. We integrate with respect to x first, moving from the left boundary to the right boundary, then integrate the results with respect to y. To set up the integral, we identify the lower and upper bounds for y, which are constant c and d. Then, we determine the inner limits for x, which are functions of y representing the left and right walls. This is our iterated integral. Notice the order: dx is inside because we are summing across the horizontal strip first. The outer integral dy then accumulates all these strips from the bottom constant c to the top constant d. When performing the inner integration with respect to x, we treat y as if it were a constant. We are essentially finding the area of a cross-section of the volume at a specific horizontal level. Once the inner integral is solved, we are left with a function of y. The outer integral then sums these values along the y-axis, providing the total volume or area of the defined region. Let's solve an example. We want to integrate over the region bounded by y equals x and x equals y squared. For horizontal slicing, we solve both equations for x. Our boundaries are x equals y squared on the left and x equals y on the right. The region starts at y equals 0 and ends at y equals 1. For any given y, x starts at the curve y squared and ends at the line y. We will integrate the function f xy equals x plus y. First, we integrate x plus y with respect to x. This gives us x squared over 2 plus xy. We then substitute our upper limit y and our lower limit y squared into the x variables. After substitution, we simplify the expression. Combining like terms, we get a polynomial in terms of y. This expression represents the area of our horizontal slice at any height y. Now we perform the final integration with respect to y from 0 to 1. Applying the power rule to each term, we prepare to evaluate the definite integral at the boundaries. By plugging in 1 and 0, we find the final value. The volume under the surface over this specific region is 3 over 20. Horizontal slicing made this setup very straightforward. Always analyze your region before starting. If the left and right boundaries are easier to express as x equals a function of y, or if vertical slices are interrupted by corners, horizontal slicing is your best friend. Be careful! If the left or right boundary changes its functional form midway, you must split the integral into two horizontal regions. Always sketch the region to verify the limits remain consistent throughout the interval. To summarize, identify your constant y bounds, determine your x functions for the left and right sides, and set up your iterated integral with dx on the inside. This systematic approach ensures accuracy in multivariable calculus. Let's test your knowledge. For a region bounded by y from 0 to 2 and x from 0 to y plus 1, the inner limits are 0 to y plus 1. Great job mastering horizontal slicing. Generated by Vision Solve AI.